Bismillahirrahmanirrahim. We are now going to discuss Poincare Bendixon Theorem from a different perspective. Early on, we saw the statement of Poincare Bendixon Theorem and we saw that it is quite easy to understand intuitively. However, it was quite difficult to make or find a region R which encloses or traps the system trajectories. We saw the example of glycolysis and constructed the region that contained the limit cycle. Now we talk about another method through which we can more easily find out the region which contains the limit cycle. Okay, so here it goes. Let us consider a simple closed curve v of x is equal to c, right? For example, you could take x1 square plus x2 square is equal to c, which is a circle. You could take x1 square over a plus x2 square over b is equal to c, which is an ellipsoid, right? And consider the system trajectories along this closed curve. The only requirement over here is that v of x is continuously differentiable. So let us suppose that this is our region. It is given by the curve v of x is equal to c, and we want to see whether a limit cycle exists in this or not. So if we consider the gradient vector v of x, gradient of vx, then we know that it points towards the direction of maximum increase. So if at this point x, our trajectories are pointing inwards, then the projection of gradient of v along this vector field f of x is going to be like this, right? So we drop a projection and we are considering this blue part over here, this blue and thick part. So this is given as gradient of vx dot f of x. And we see that if the vector field is pointing inwards, then this quantity is negative, right? On the other hand, if this quantity is pointing outwards like this, f of x is like this, and here we have our gradient vector pointing towards the direction of maximum increase, then the projection of gradient of v along this vector, which is this small region, so this is going to be greater than 0. We see that it is pointing towards positive x-axis, right? Early on, this projection, this was pointing towards the negative x1 axis. So we saw that if the vector field is pointing inwards, so we can write it here, f of x pointing inwards of v of x. Here we write f of x pointing outward so in that case and similarly if f of x is tangent to v of x, right? So if I try to make such a situation, it is going to be somewhat, I make another curve within this to depict this, right? Let us say that it is another v of x is equal to some c, and you see that the vector field is tangent to it at some point x. Now, the gradient vector is as usual pointing towards the direction of maximum increase. It is like this. So we see that if we take a projection of gradient of v along f of x at this point, then this is going to be 0. So the third condition is okay. So we have made an important observation over here that if we have a region given by v of x is equal to c, then the trajectories are going to be trapped inside a region whenever gradient of v dot f of x is less than equal to 0, right? So if they are going to be less than 0, it means the trajectories on the boundary of region V are pointing inwards, whereas if this is equal to 0, then it means that the system trajectories are actually tangent to the curve V at its boundary. Similarly, we could also consider another region, annular region given by M is equal to W of X is greater than equal to some C1 and V of X is less than equal to some C2, and we could say that the C1 and C2 are greater than 0 and trajectories are trapped inside M if gradient of V dot f of x is less than equal to 0 on V of x is equal to C1 and gradient of W dot f of x is greater than equal to 0 on W of x, sorry, this was C2 is equal to C1, and the condition is that C2 is greater than C1. So if I illustrate this in the form of a figure, so we have a region like this. This is V of x is equal to C2. This is another region, W of x is equal to C1. And we are saying that the trajectories are either parallel to or moving inward from the boundary of this V1. Whereas for of the V of x. Whereas on the inside, we are saying that the trajectories are moving outward or parallel, tangent to the second curve, W of x is equal to c. We now have a region given by two curves, W of x is equal to c1 and V of x is equal to c2. So the trajectories are trapped somewhere within this region, in between this region, right? So this outside was actually made erroneously. So the system trajectories are somehow behaving like this. So that is how we can find the trapping region R for satisfying the conditions of Poincare Bendixson theorem. We can now look at an example, and that is then going to conclude how we actually apply this. Let us consider that we have a system x1 dot is equal to x1 plus x2 minus x1 square plus x2 square. An important observation that I would like to give is that whenever you find something that resembles the equation of a circle, then it generally points out that the system is going to have a limit cycle. It is not mandatory, but most of the times it happens. And what you can do is, if you can convert the system into polar coordinates, then maybe you can see that actually there is a limit cycle within the system. Okay, so for this system, we want to find out, first of all, whether a limit cycle exists, and if a limit cycle exists, then we want to find out the potential region R in which this limit cycle exists. So first of all, what we do is we calculate the Jacobian matrix and the equilibrium point, and we want to see that what is the nature of that equilibrium point, right? So if you calculate, then you can easily find that the equilibrium point x star is equal to 0, 0. The equilibrium point is at the origin, whereas the Jacobian matrix partial f over partial x is given like this: 1 minus 3x1 square minus x2 square, and 1 minus 2x1 x2, and minus 2 minus 2x1 x2, 1 minus x1 square minus 3x2 square. And if we apply x1 x2 is equal to 0, 0, then the resultant matrix is 1, 1, minus 2, 1, and we know that this matrix A, if we want to just find out its eigenvalues, then we know that the determinant of A is equal to the multiplication of the eigenvalues, which is equal to 1 plus 2 is equal to 3, right? So, and this is positive, so which means that either both of the eigenvalues are negative or both of the eigenvalues are positive, right? So, if we calculate the eigenvalues, then lambda 1 comma 2 is equal to 1 plus minus square root of 2, right? So if we see using the Newton's direct method, then the nature of this equilibrium point is a unstable focus. It is a complex eigenvalue, and its real part is greater than 0. Right? So this is unstable. Okay. Now, what we have established that there is one equilibrium point within the system, and that equilibrium point is an unstable focus. So one of the conditions of the corollary of Poincare Bendixson theorem is satisfied. We now want to find out whether there exists a region, or we want to actually find out the region in which a limit cycle exists, right? So for that to happen, we have seen that gradient of v dot f of x should be less than or equal to 0 for some v of x is equal to c, such that v belongs to c C infinity, which means that it is continuously differentiable and smooth as well. Okay, so let us suppose that we have taken this function. So we consider partial v over partial x1 times f1 of x plus partial v over partial x2 times f2 of x. Just to point out what is f1 of x and f2 of x. So if this is the complete vector field f of x, then x1 dot is equal to f1 of x, right? So it is a vector of these functions. So this is from where f1 and f2 are obtained. Okay. So if we calculate this, this is given as, this is quite a long expression, so I'm going to write it downward over here to x1 times x1 plus x2 minus x1 x1 square plus x2 square plus 2x2 times minus 2x1 plus x2 minus x2 times x1 square plus x2 square. So what remains is only simplification of this thing, and it comes out to be 2x1 square plus x2 square plus 2x1 square plus x2 square whole square minus 2x1 x2. Right, so we make an important observation over here that we note from elementary algebra that x1 plus x2 whole square is greater than equal to 0, and if we expand this, it is going to be x1 square plus x2 square plus 2x1 x2 is greater than equal to 0, and this means that x1 square plus x2 square is going to be greater than equal to minus 2x1 x2. So why we did this? Because we had everything over here captured in the form of x1 square plus x2 square, and we did not write over here, but we were actually considering v of x is equal to x1 square plus x2 square is equal to c, and the aim was to find the value of this c for which this the trajectories remain trapped inside this. Okay, so if we replace this quantity with this, then the resulting equation is going to be somewhat like this: 2x1 square plus x2 square minus 2x1 square plus x2 square whole square. And since this quantity x1 square plus x2 square is greater than equal to minus 2x1 x2, it means that we are going to add a bigger quantity than this quantity in this, and therefore this equality sign over here is going to change to a less than equal to, because now we are adding a bigger quantity than the original quantity over here. So we add like this. Okay, and this is less than equal to 3c square, 3c minus 2c square. Okay, so we have got a condition gradient of v dot f of x is less than equal to 3c minus 2c square. And we saw that whenever gradient of v dot f of x is less than equal to 0, then actually v of x is that region. V of x is equal to c is that region in which the trajectories remain inside. Or rather, we should say that v of x is equal to c is the boundary of that region that traps the trajectories. So what we now do is we try to calculate this c, and from here we see that the trajectories remain trapped inside this if right. So what we have essentially calculated, we started from v of x is equal to x1 square plus x2 square is equal to c, but we did not know that what size or what radius of the circle should be that is going to trap the trajectories inside it, or where the trajectories are going to be located. So we calculated gradient of v dot f of x, and we tried to employ this inequality to find out this value of c, and we found that c is greater than equal to 1.5. So it means that whenever we are going to construct a circle with a radius greater than equal to square root of 1.5, the trajectories are going to be trapped inside. So if we make the first portrait of this system, then here is an origin, and this is unstable, so the trajectories are moving, spiraling away from it like this, and this is the region, right? This is the region with radius, that's how we plot the radius. Radius is equal to square root of 1.5, and up beyond this, the trajectories are pointing inwards, right? So if we conclude that outside this region, the trajectories are pointing inward, and within this region, there is an unstable focus due to which the trajectories are emanating away from the origin, then we can safely conclude that this region's v of x is equal to c with a radius of square root of 1.5 is the point where the trajectories actually become tangent to this circle and keep moving here. So this is essentially the location of the limit cycle. So not only we have established that a limit cycle exists because we were able to find a region that traps the trajectories, we have actually located the limit cycle as well. So this is how the Poincare Bendixon theorem is applied in practice. I hope this is going to help you. Thank you.